Place a 1970s machine in a universe whose background glow is only 2.7 Kelvin above absolute zero, and you would expect it to freeze long before its 49th year. That sounds impossible. Deep space seems like the obvious killer, nearly minus 270 degrees Celsius, no sunlight worth depending on, and an aging spacecraft built before personal computers and smartphones became ordinary household objects. Surely every wire, fuel line, and circuit board should have gone cold and silent decades ago. Yet Voyager 1 launched on September 5, 1977, entered interstellar space in August 2012, and is still operating. So the real question is not simply how it resisted the cold. We need to follow its energy where heat enters, how it moves, where it escapes, which systems still receive power, and what will finally end the conversation with Earth. The first correction begins with that terrifying temperature. NASA's COBE mission measured the cosmic microwave background at 2.725 Kelvin, about minus 270.4 degrees Celsius. The number is real. The picture it creates in our heads is not. We imagine Voyager submerged in an invisible ocean of freezing air. But the cosmic background is faint radiation filling space, not a dense fluid washing across the spacecraft. A thermometer can tell you how cold a freezer is, but that number alone cannot tell you how quickly something inside will cool. You also need to know what is touching it and how its heat can escape. On Earth, moving air is very good at carrying heat away. Stand outside in a winter wind, and the air constantly replaces the thin, warm layer next to your skin. That process is convection. Voyager has almost no surrounding material available to do the same thing. Space cannot blow the spacecraft cold. That does not mean objects cannot cool in a vacuum. Heat still conducts through Voyager's solid structure, moving from warmer components into neighboring materials. Its exterior also releases energy as infrared radiation. But without an atmosphere, one of the fastest and most familiar escape routes for heat is missing. Voyager is therefore less like a person trapped in an Arctic storm and more like a warm object inside the empty, reflective gap of a thermos. The insulation is not perfect. Energy still leaks away. The difference is that engineers can influence how quickly it leaves. Multi-layer insulation reduces unwanted heat exchange. Surface coatings, radiators, and thermal louvers affect how readily different areas absorb or emit energy. Protected sections can hold warmth longer, while other surfaces help unwanted heat escape. The spacecraft is not one frozen metal block. It is a network of thermal paths. That brings us to a relationship established by physicists Joseph Stefan and Ludwig Boltzmann. The Stefan-Boltzmann law tells us that a warmer surface radiates energy much more strongly than a cooler one. A hot stove gives off energy far faster than the same surface after it cools. Even though Voyager's radiation is mostly invisible infrared rather than visible light, this changes the problem completely. Voyager does not cool at a fixed rate determined only by the temperature of deep space. Its temperature settles through a running energy balance: heat generated inside, energy absorbed from outside, heat conducted through the structure, energy retained by insulation, and infrared radiation leaving the surface. Think of a blanketed house with carefully chosen places where heat can escape. Close every opening, and the house may become too warm. Open too many, and important rooms become too cold. Voyager must do both jobs at once: retain enough heat for vulnerable hardware while rejecting energy that cannot safely remain inside. So cold is not always the only danger. A spacecraft in vacuum can overheat when generated or absorbed energy cannot escape. But for late-life Voyager 1, the documented pressure is now moving in the other direction. Its available electrical power is declining, and less electrical activity also means less internal heating. The source of that energy sits on 3 long booms, Voyager's multi-100-watt radioisotope thermoelectric generators, or RTGs. Each produced about 158 electrical watts at the beginning of the mission. Roughly 474 watts combined, Even at launch, that was less electricity than many household appliances use. The generators are not miniature reactors running turbines, and they are not one giant furnace directly warming every instrument. Plutonium-238 decay creates heat. Thermoelectric devices convert part of that heat flow into electricity. The remaining thermal energy must still be managed and released. A useful mental image is a set of extremely long-lived, heat-powered batteries. They work without sunlight, which is exactly what Voyager needs so far from the sun. Their electricity runs computers, communications equipment, instruments, attitude control, and heaters. The powered electronics themselves also release heat into the spacecraft. For decades, that system made Voyager look almost immortal. The vacuum prevented familiar convective cooling. Insulation reduced unwanted radiative loss. The plutonium supplied energy continuously. Hardware kept working at temperatures beyond those for which it had originally been designed. But the generators cannot hold the electrical budget steady. NASA reported that the 3 RTGs together produced about 225 electrical watts in 2023, and each Voyager loses about 4 watts of usable electrical output every year. 4 watts sounds trivial until the entire spacecraft is already surviving on a tiny allowance. It is like permanently removing the power of a small nightlight from a small house every year, then deciding which room must go dark next. There is no reset. The missing watts do not return. This is where the story stops being about whether space is too cold. The real struggle is whether Voyager can keep the correct parts at the correct temperatures while its electrical budget collapses. Turning off a heater saves electricity. It also removes heat from the area around it. Turning off an instrument reduces demand, but the instrument no longer releases its own waste heat. Every shutdown changes 2 columns in the spacecraft's account at once: power consumed and heat distributed. That is why asking, has Voyager frozen, gives us almost no useful information. Voyager does not have one temperature. Each instrument, electronic bay, fuel line, and mechanical assembly has its own thermal connection and its own survival limit. In 2011, a nearby heater was switched off. Voyager 1's ultraviolet spectrometer later continued operating below -79 degrees Celsius, even though it had originally been designed to operate only down to about -35. One part of the spacecraft survived a temperature below the coldest naturally recorded outdoor air on Earth. That sounds like victory, until we look at another part. JPL thermal engineer William Ledebor and the Voyager thermal model team reconstructed the spacecraft's late-life thermal behavior decades after launch. Their model identified declining temperature margins in propulsion lines and the risk of hydrazine propellant freezing near 1.6 degrees Celsius. One instrument can operate tens of degrees below zero, while a fuel line may be threatened at a temperature similar to the inside of a refrigerator. That is not a contradiction. The components are made differently, connected differently, heated differently, and asked to perform different jobs. Now the engineering choices become painfully specific. We might want to preserve every scientific sense Voyager once had, but the spacecraft began with 10 principal science instruments and no longer has the power to support them all. Engineers must decide which capabilities justify their electrical and thermal cost. Voyager 1's cosmic ray subsystem was switched off on February 25, 2025. On April 17, 2026, JPL switched off the low-energy charged particles experiment to conserve power. As of that date, the spacecraft was still returning science from its magnetometer and plasma wave subsystem. That does not mean only 2 systems on the entire spacecraft remain powered. Computers, communications hardware, attitude control, and other engineering functions are still necessary. But scientifically, Voyager has become a smaller machine. 2 senses remain focused on interstellar space. The apparent possibility has not disappeared. Plutonium-238 decays slowly. Vacuum still prevents ordinary convective cooling. Insulation still slows unwanted heat loss. Some hardware has already shown remarkable resilience beyond its original operating range. By removing non-essential loads, engineers may keep the most valuable functions alive longer. The price is that every extension contains its own loss. Save one instrument by turning off another, preserve communication by surrendering a heater, protect the remaining power margin, and another region of the spacecraft cools. The strategy works only while the remaining energy is enough for every system that cannot be sacrificed. Eventually, science collection may end while basic engineering data continues. After that, the final priority is the connection itself. Voyager normally sends X-band telemetry at only 160 bits per second through a 3.7-meter high-gain antenna that must remain pointed toward Earth. The dish is wider than a small car. Yet the data stream is astonishingly thin at that rate. Transmitting the equivalent of a 1 megabyte file would theoretically take roughly 14.5 hours before communication overhead or interruptions. The radio waves travel at light speed. The data rate is what remains slow, and the distance makes every exchange feel less like a conversation and more like leaving messages across time. On November 18, 2026, Voyager 1 is projected to become the first human-made object one light day from Earth, about 25.902 billion kilometers away. A command sent on Monday would not arrive until Tuesday. Even with an immediate response, the earliest reply could not return until Wednesday. Maintaining that link requires more than a working transmitter. The spacecraft must still produce enough electrical power, keep essential electronics within survivable limits, control its orientation, and hold the antenna toward a planet that has become an almost unimaginably distant target. NASA says communication might remain technically possible into the 2030s, perhaps through approximately 2036, depending on available transmitter power, but that is not a promised final date. The actual ending depends on how the remaining power supply and aging hardware behave. The scientific reversal is now complete. Vacuum helped Voyager avoid rapid cooling. But vacuum cannot create energy. The plutonium continues producing heat. Yet the usable electrical output declines. Each shutdown saves power, but alters the thermal balance. The machine survives only while every indispensable flow remains within an acceptable range. Voyager's final enemy is therefore not simply cold. It is not simply heat, either. It is the point at which the spacecraft can no longer divide a finite and shrinking supply among communication, attitude control, computers, surviving instruments, and whatever thermal support remains essential. When Earth can no longer hear Voyager. The voyage itself will not suddenly stop. The mission and the object will separate. Its present trajectory carries it onward at about 3.5 astronomical units per year, in the year 4272 AD. Voyager 1 is projected to pass within about 1.7 light-years of the star AC plus 79 3888. Even that relatively close passage misses the star by more than 100,000 times the Earth-Sun distance. It is not a visit. It is simply motion continuing after communication has ended. So return to that imagined 1970s machine beneath a 2.7 Kelvin sky. It did not survive by defeating cold with one enormous heater. It survived because engineers controlled where energy was generated, where it moved, where it escaped, and which systems received the final watts. One day, the power column will fall below what the connection demands. The radio line will vanish. Voyager will no longer be able to tell us its temperatures, its measurements, or even whether its remaining systems are still functioning. But silence will not mean that space finally stopped it. It will mean Voyager no longer has enough energy to tell us that it is still going.